So we started out looking at H2, and there's a lot of terms in that equation. Could we go possibly, is there a simpler diatomic molecule? And the answer is yes. If we take away one of the electrons, we'll still have a molecule, H2 plus, an even simpler molecule. And you may think, well, this doesn't have enough electrons, it can't actually form a real molecule, but that actually isn't correct. So even with only one electron, normally we think of, we have to have a pair of electrons in a bonding orbital or whatever. H2 plus forms a stable molecule, and it exists out in space, and it's been measured many times by astronomers. And so this is an actual molecule that exists. This isn't just a theoretical exercise. But the Schrodinger equation becomes much simpler because we only have one electron to worry about. We don't have any electron-electron repulsion terms. We just have the repulsion between the nuclei. So that still makes this a system that we can't solve exactly, but we can still write it the Hamiltonian, and it's a lot simpler. Instead of 10 terms, we only have 4 terms. So if we write this, I'll switch back to atomic units so we don't have all of the extra masses and whatnot. So we'll have a -1/2 del, and I'll be specific, this is del of the electron squared. And this is simpler as long as if we ignore the motion of the nuclei. So this is using the Born-Oppenheimer approximation. So I'll write that as the BO approximation. All right, so we see there's only one kinetic energy term, and that's because we're ignoring the motion of the nuclei. All right, so then we'll have a repulsion term from the electron with nucleus A, a repulsion term from the electron with nucleus B, and then we'll have, attractive term, nucleus A, nucleus B, and then a repulsion term between the two nuclei, and we'll write this as capital R. Again, this capital R being the bond length, the distance between the nuclei. Okay, so then our Schrodinger equation is this, H psi equals E psi, and the question is, of course, what we're always after, what is the wave function? What do the wave functions look like for this? And one thing we'll see with this is that we end up, just like we did with atoms, we have atomic orbitals. The solutions give us molecular orbitals. So these are wave functions for the electrons that stretch out over the whole molecule. And this is a key idea with diatomic and larger molecules as well. The wave functions that describe the electrons in these systems sometimes are localized on specific atoms, but in general, especially for the valence electrons, these wave functions spread out over the whole molecule. And so this is something we'll see with these diatomic molecules, and also something we'll see as we get to polyatomic molecules. Now, how are we going to solve this? Well, we need to use some sort of variational theory or perturbation theory approach. So we'll look at a variational theory approach. All right, and so we need a trial function. And one common trial function that's used in this sort of idea when we're looking at molecules, so just to be clear, this is a variational theory, is to take our atomic orbitals and add and subtract them, right? Take what we call linear combinations of atomic orbitals. And this is a approach that's still used. Even in computational chemistry approaches, generally we start with the idea that we have atomic orbitals and we add them together and subtract them to form our molecular orbitals. So this is abbreviated LCAO, linear combinations of atomic orbitals. And so we can make two different wave functions. Say if we're looking at just the ground state, so at the lowest energy, we have a 1s orbital on nucleus A, centered on nucleus A, and a 1s orbital centered on nucleus B. And we can combine these. So we can make two different wave functions out of this. We'll have some C1, some coefficient times our 1s orbital on nucleus A, and we can add and subtract that. Right, so add or subtract it with some portion of a 1s orbital on nucleus B. All right, and this is a general pattern we'll see, is that however many atomic orbitals we put in, that's how many molecular orbitals we get out. So 2 atomic orbitals leads to 2 molecular orbitals. So we can call these AOs and these MOs. Okay, and so this will be our usual starting point for molecular orbitals. Now, what do these look like? We're just going to look at the solutions to this. Your textbook goes through a lot more detail on how exactly we solve this and what the exact wave functions look like. We're more going to look at like the general properties of the wave functions and what it can tell us in terms of chemistry. And so we'll look at that in the next video.